I'll turn the mic on. Good afternoon!
Good afternoon.
Excellent. Okay, so my name's Andy. I'll be talking to you today about hopefully making simplifying thread safe code. Right, that's the idea behind this. We'll be targeting .NET 4 and 4.5. We'll be touching on some of the stuff, new stuff that's coming out in NuGet, talking about the musical collection and that kind of stuff. My name's Andy. This is Richard. Richard's my code monkey. He'll do everything he possibly can in his power to divert the demo from the one true track of goodness. Okay, so we'll try really hard to see how Rich does with that. I'll click my fingers. It's no disrespect for Rich, but it just means answer the slide. That's all it is. I'm not being rude to Richard on any comments. He was very discourteous to the monkey. No, I'm not. Okay. So, like I said, the idea of this talk is really to have concurrency without complexity. And that's the plan. And then if you write multi-threaded code, you can have no complexity, but you probably end up with what? It doesn't always work right. Okay? So you don't quite have the locks in the right places, and you don't use the right data structures at the right times. And so you might run really fast, but maybe occasionally it will break when you're doing that demo, all that kind of stuff. So what we're going to do is try and keep the simplicity, but get the right, basically get the right result. So we're going to kick off really going to talk about some motivation. We're going to write some code, hopefully, that we're not going to use any of the simplified stuff. We're going to make something quite complex. And then we're going to throw in some of the goodness. So we'll throw in lazy T, start playing around with concurrent collections. Have we played lazy T before? A few of you? Concurrent collections? Yeah, quite a few of you. I might not get as far as doing anything today, synchronous collections today. We'll see how we go for time, depending on typing ability. We won't get to it. Immutable collections. Have we played with the new goodness from Microsoft with immutable collections? 2 people. Immutable list. Does it sound exciting? What if you add something to an immutable list? What do you get? A new list, right? If it's immutable, you can't actually add to it. So it seems a bit odd, doesn't it, really? Okay? But we'll see that effectively, actually, in some scenarios, it can be quite effective. Okay. So, like we said, single-threaded, multi-threaded code, ultimately, if you're sharing state, you have to pick some kind of synchronization primitive in order to make sure your code's through. So we've got a whole variety of ones that we can effectively use. We've got things like read and write off. We can do some stuff like double check locking various things. But often it reduces some kind of complex kind of code. Obviously, the point where we do have to put locks and stuff is where we have beautiful shared state. One of the goals in multi-threaded code is to get rid of that. No shared state, or better still, immutable shared state. If we can write code where all we're ever doing is reading from immutable data structures, then life does get really simple. So that's really where we're going to try and end up today, trying to write stuff more and more with immutable stuff, so we don't have to use locks or anything like that. Let's write code, because that's really what we're camping for. No one wants to see slides, do you? Anyone want to see slides? No. There we go. You know, you ask a question, all answer. Right, so you're already running? Failed already, hasn't it? Solution Explorer. Remember we talked about this, didn't we? Okay. Okay. So this is this called project. Right, okay, so set that as the start project. Which one's also mine we start? This one? Okay, can you just bring up progress sketch real quick? Slow down, pass the person pass. Your mouse working? Excellent. Well, start. Okay, so we've got this class here called a CSV repository. Can you all see the code from the back?
Yeah.
Yes? Okay. Give it a directory, it's going to load every CSV file from that directory into memory, and it's going to store it as a list of string array. Okay, are we cool with that? Okay? And up here, I've got a little strategy here that is what this piece of code is going to delegate to load a particular file. The only reason for doing that is I want to count how many times a file is loaded. Okay? Yeah, so this piece of code here won't go to the file system directly. We'll pass in the strategy. This piece of code here is responsible for loading. It's just keeping a count of how many times it was called. Okay, all good? Okay, if you go down here, we've then got some code here for each loop. We've got one thread of execution. It's taking it's asking for all the CSV files one by one, and it's basically projecting them into a series of objects. Okay, all happy with that? Run the code. Fantastic. Control F5. Good. So it's loading all these CSV files into them and process them, and eventually it's loading 37 CSV files. Okay? Now, the fact that in the constructor for the repository we're doing the load operation, even if we start throwing multiple threads now, so go and undo the parallel.for, So we've got parallel.for. Everybody cool with parallel.for? Yeah, it's going to do that looping parallel. So basically we're going to kick off potentially 10 tasks, where 10 tasks are all going to try and hit the repository. Okay, but because we've all preloaded everything, we should only still only load 37 times. Okay, right? And hey, press a lot more stuff on the screen as we process the one in parallel. We've got 37 still loaded. Okay, all good? All happy with that? Okay. The goal of a lot of these demos now is to keep seeing loading 37. Okay, but we're going to make it a little bit more complicated. Because the code at the moment, inside the repository, when you create the repository, goes to the file system and preloads everything. If in our actual use case, we don't use all the CSV files, okay, that's kind of a waste. And then maybe we want to load them as we need them. Okay, so we don't really want to preload them. So up here we've got a private dictionary string and list of string array. The key to the dictionary is the name of the file. The list of string array represents the file, where the string array represents each row. Okay, so a list of that. So somewhere down here you've got a 2 dictionary. Comment out the 2 dictionary. Yeah. And change it to a 2. Right, copy it. Copy the line. No, just the line. Just the line we commented out. That's it. You want to use that keystroke, but you know you shouldn't. Copy the hard one. Okay, cool. Okay.
Well, I think we've done pretty much.
Yeah, and then check, instead of loading the data there, just pull that out to the clipboard. Yeah. And the 2 lists. Yeah, cool. And you just create a null but cast it to a list of string array. So now what we're going to do is we're going to build a dictionary, but we're not actually going to load the data. Okay? And when someone asks for the file, we'll go to the dictionary and say, is the dictionary value null? And if it's not, what are we going to do? Remember, which in his previous talk said, this point where I pause isn't because I forgot what to say. This is your contribution bit. This is how I know that after that big lunch, you're still alive. Okay? So what are we going to do if it's null? Load it. Excellent. Okay, so comment that line out, Rich. This is the original code. At the end of all this, we're going to get back to some very similar things. So inside here, it's going to say list of string array, CSV rows, equals CSV files, data file, okay, and then after that can we say if CSV rows equals null, go up and say CSV rows equals load data, and load it, excellent, good clipboard, perfect, and then say CSV file, square bracket data file,
inside the field.
Yeah, inside there.
Oh, hold on, is that field? What's that? That's data file.
If you would, you just finish. Right. Okay, yeah, and then CSV files, square bracket, data file, equals CSV rows. Brilliant. And then take that projection from the dot skip and return it. So take that, and just return it. So say return CSV rows, dot, 3, 5. Okay, so it compiles. It's going to work. Is it going to crash? How does everything is going to crash? No one. Go run the code. Boom. Okay, scroll up. What the thing is? It's a, we know what the exception is? Exception is modified. So you go back to the code. Where you ask it for the files, scroll up. You simply return the keys from the dictionary. We're iterating through that. We're modifying the dictionary while we're iterating. Can't do that. So just put a .2 list on the end of that. So we're making it now, so we're returning a copy of the keys, which means you don't pay to iterate through a copy, that's fine. Yes, that's one technique we can certainly use for thread safe. So now look, is life good? Why not? 50, run it again. The rule of these demos is we're going to run every piece of code 3 times. If it works 3 times, as far as we're concerned, we check it in. Just like we do at work, right? That's what we do anyway. 3 times is the rule, we check it in. So if this isn't good, so what are we doing at the moment? What's happening? Yeah, I mean, this is what's happening. 2 threads are coming in, both threads are seeing that it's not in the dictionary at a particular point, both proceeding to load. one loads it, the other one's loading it, the last one to load it is probably the one that's going to end up assisting it for everybody else to share from that performance. That's not what we want to do. We basically want to make sure that we only load it once. What would be the easiest way to guarantee that? Put a lock in, yes. So go and wrap all that code rich in a lock. Now below that comment, talk about
There.
so lock. What are we going to lock on? No, we're not locking on this. We are bad today, we are bad. CSV files. Embrace it around that point? Yeah, excellent. Okay, is that going to work? You need to promote that variable. No? Yeah, because we refer to it down below. Yeah. Just put that up there. Equals not. Go then. Yeah, then. Yes, it should be right. Okay, is that going to work?
No.
Yes, no? Yes, no? Anybody not sure? One person? You should run it? 37. How many times? 3. 37? 37. Should then. So this works, right? This is Fred's same code. Why is it not good?
Everything's contended on the same lock.
Yeah, everything's contained on the same lock at this point, right? So first of all, everything's contained on the same lock. Also the fact that, how many files can we load at any one time? 1. So that's not good. So I guess we could argue that a possible improvement would be, well, we know that we shouldn't have multiple threads touching the dictionary at the same time because the dictionary class is not thread safe, so we definitely shouldn't do that. So maybe what we'll do this time, Rich, is put one lock around that bit, the CSV rows bit, where we go and look inside the dictionary, so close it off before the if. Okay. And then inside there, put a lock inside there. Well, put it around the CSV file dev file is to be
Absolutely, just a good place.
So we could do that. Is this any better? We still want lock, but it's going to contend for one lock. Is this any better?
Yes. But we don't lock on the file, we can lock on the row.
Yeah, we're not. We've just got this single lock on the thing. So what's going to happen now is when it comes into here, it's going to touch the dictionary. Is it in the dictionary? If it was in the dictionary, great, it would be turned out here. If it's not in the dictionary, it'll proceed to this block of code and load it. It will then, before updating the dictionary, get the lock again. It's thread safe, but do we still have a race condition? Is it possible we could load the same file more than once? Yes, because between checking here and here, maybe, yes, well, that's right. 53, again. Yeah, 52, again. So clearly, this is not good.
We also able to install the R toolbar.
Did we?
It's still updated.
Oh, okay. Oh, wow. Thanks for stopping that, Rich. I appreciate that. Okay, so this is really what we want to do is have a lot more fine-grained locking. We'd like to lock on each CSV file. That would become cool. However, if we go up to our dictionary is of what? It's basically of nulling. You can't lock on null. Okay? We don't really get access to the key objects to be able to lock on those. So what we could do at this point is we could actually put a cheap object here. So rather, loading the file is expensive. We don't want to do that. Let's just put a cheap object. So we're going to create a new class called a lazy CSV. And that's going to have a public property of list of string array called value. So, no, not pop, just field. Let's be daring. Yeah, list of
String.
Yeah, list of string. Okay, and let's call it value. And let's just make it that field. Now, how quick is it to create those bad boys? How quick is it to create an object.net? Really quick, right? So creating those is not really expensive, right? And if we never use it, no biggie, right? It's not that much resource. So now what we're going to do is change that dictionary now. Instead of being a list of string array, yeah, it's going to be a lazy CSV. So we're just going to put a lazy CSV object inside here. Okay? And then scroll down. And here's our to dictionary. Okay? So what we do inside our to dictionary. Okay. We're going to change that to a new lazy. We're going to return it as you make. Well, we don't be sharp over here. I've got it installed on my machine.
Have you?
Yeah, I have apparently, yeah.
That's a good idea.
Yeah, I think it's awesome. What are you doing? Just have to do. Yeah. So now we've got a cheap object that we can lock on. Yeah? Okay? Through the power of the sharper. Brilliant. Okay. Right, so now we've got a dictionary of those, which means if you go down to our bottom piece of code down here. So now we're not going to lock on CSV files anymore. What are we going to lock on? CSV file, square bracket, data file. Right? So now we've got a value object inside here. Now, let's open this up a bit. Yeah, so in that CSV rows now equals CSV data files dot value. Yeah. Fantastic. Get rid of the closing lock brace. Yeah. Okay. So now what's going to happen is if two requests come in for two different files, they won't keep the same lock, right? Okay. So go through here, I think we're good, get rid of the second lock. Yeah. I think get rid of the bottom one. Okay. And then close the lock off after you've got it. Yeah. Okay? All good? Better now? What's that referring to? Oh yeah, dot value, sorry, yeah. After CSV files, square bracket. No. After the square bracket.
Oh, yes, you're right.
Yeah, because that's the. Okay, yeah? Well, what do you reckon? Is it going to work? Compile it when you ship it. 37. 2 more times. You're wasting valuable seconds. Well, is that good? Good code? And it works. What can we do better? You remember at school when you submit your homework, you put your life and soul into it and the teacher wrote, good, but could do better. This is what this is, right? It works, it's thread safe. How can we make it better? What's wrong with it? Well, what happens once if we've got lots of threads all trying to use Weather in London CSV file, once it's loaded, they still got to acquire a lock in order to proceed. Do we want to do that? And really what we want to do is to say, well, if it's already loaded, right, it's not going to change, it's immutable, just use it. Only if it hasn't already loaded do we want to lock it. So we could say here, move the CSV rows out of that. No. Leave that there. Move the assignment. This one here, this part. Above. Yes.
With that.
The bit where we assign CSV rows, move it before the lock. We see we rehearsed this. Okay. So,
Remember that there.
yeah, you got it, right? Okay. And then we'll just say if after that, if CSV rows is equal to null. So, yeah, that's it. Cool. Okay, good. Braces, yeah, excellent. Wrap that up. Excellent. Okay, get rid of the if inside out. We don't need that, do we? Inside. Just comment that out. Happy with that? So now what's going to happen is this. We come into here. If the pull the value out, if the value is non-null, yeah, then we'll basically drop out to here and we'll just use it. If the value is null, we'll lock and we'll load it. Yeah? All good?
No.
Why not?
See that they get two threads come through both no.
Run the code. 57. Every time I tried this before, it was 37. Run it 2 more times. You might have to do a really black moment. Oh, jeez. I don't know how we've written it differently this time. Anyway, so yes, there is a race condition. Before I've had to reduce it sometimes. Okay, so where's the race condition? Where's the race condition? Yeah, so basically we're checking for null, yeah, and then entering here. You could have 2 people queuing up here, one behind each other. First one wins, comes in, loads it, second one opens it. So what are we going to name it in here? We're going to put this if check back in, but not quite like that. What are we going to do? We're going to re-get that CSV rows. So go get it again. Okay, take the line where we pull it out from the array. CSV rows will always be white. Above, 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 up, 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 up. Stop. Copy that line and copy this other one. I've seen the top. Okay, so what's this pattern called? Double check locking. Compile it. 37. 2 more times. 1 more time. So that works. Now, this was the line we started with. On with that. This is what we replaced it with. Which one's more complex? And you have to say the bottom one, otherwise the rest of them is dead. Okay, there's no point. Yeah? This is way too more complicated, yeah? We do a lot more stuff. It's harder for someone to read and understand. The other bit was a nice simple bit of link. Link is lovely. We like reading link, it's nice and easy. I want to replace all this so that it looks exactly like that. Okay? And to do this, we use a type called lazy T. Okay? Now, lazy T basically is going to simulate our lazy CSV file. It's an object that's cheap to create. Go back to Program CS. Yeah, change that to old main and create a new name. Lazy T is a cheap object. But it's a lazy T. You can be lazy of anything, an integer, a person, whatever type you want. That type is typically an expensive object to create. What lazy T provides is a wrapper around it. And effectively, when you ask for the value the first time, it will then create the value. So it's lazy creation of T. It will guarantee that lazy T is created in a thread-safe way. If multiple threads ask for it, and it's in the process of creating on another thread, the other thread will be told to wait. When it's created, they'll all share the same value. So, here's a simple one. Create me a lazy person. Yeah. Then initialize it, lazy, let's do lazy dot value. Yeah. Dot name equals rich. So we go on, lazy dot value dot age. How old do you reckon Rich is? Shaq, quick.
22.
22. There's no prizes in this talk. 22. If you don't hex, you'll be far off. Okay, well, actually, we'd actually be very happy about it. Then just do for me, console right line, lazy. It's got two string implementation. Okay, and can you just, can you print out, after you declare the lazy, we'll just print out variable declaration. Okay, so when we run this code, we're going to create this cheap lazy object. Okay? The first time we call the value property of the lazy object, it will create us an object. When we call the value again, we'll be using the same object. And if this happens across multiple threads, we'll always get back to the same object. Okay? Scroll up, let's just look at the shown person. Person inside the constructor has created. Okay? So we know where the constructor file. Scroll down. So on the screen, we should see what? Declaration done, created, and then the value. Run it. So declaration done, then created, then name is rich. Okay, all good? Okay. Go and change it, go up to the top, change the constructor of person to take a string. And then assign the name to that. Okay, so name, through the power of the initialize all the property name. Yeah. Excellent. Okay, all happy with that? Okay. Will this compile? It will compile. And that's the scary bit. Compile. It compiles. Is it going to run? Lazy initialize type does not have a public parameters constructor. So at the point when it tried to create it, it says, whoa dude, you don't have a public parameters constructor. And therefore, I can't create you. So lazy T by default only works with has to have public constructors. It's using reflection to do creation. What we can provide here, and it's almost definitely the preferred way of doing it, because you really don't have lots of code using reflection, is effectively to provide a lambda here. So it'll take a function of T, and you provided the construction logic. Okay, so go and run this now. And you just do. Yeah, all happy with lazy T? Hopefully that will find little light bulbs in your head to say, all that horrible code that we just wrote previously, we can radically simplify, right? We go back to our original dictionary, okay, scroll to the top. Instead now, we're going to have a dictionary of lazy of CSV, we're going to have a dictionary of lazy, of list, of string array. Okay, scroll down. And then comment out your, right, I'm missing one. One more. So much shit. Okay. Scroll down. Comment out your two dictionary. Okay. Now copy the bottom two dictionary. That's probably the one you want mostly. Okay. What do you want to do here now? Instead of loading the data immediately, we're going to create what? We're going to create a lazy object to put into the dictionary, right? The lazy object is going to take a function that's going to do what? Load the data. Okay? The first time you hit the value on the dictionary, it's going to... Oh, okay. Lazy goes of, yeah, list of, should we write? Open bracket. Okay. Go open, close goes to. Yeah. No data. Name, no data. Good. It's all closed off right. Are you missing any close bracket operations? Okay, what happened with that? We create these cheap objects that when tasked for their value will load the data, and it will load in the thread state way. If it's in the middle of loading the data and someone walks up to the same lazy object and says, give me your data, it says, right. The moment this guy's finished, the other thread gets the data. Okay? Scroll out. Delete or comment out that block of code, don't delete it because we swear it out around. Okay, copy the line above. Uncomment it. Instead of saying CSV dot do dot, that's the only change. Is that as easy to read as the original? Totally. Is it thread safe? Totally. Okay? Yeah, we can't do it. We don't do that. We have time ready? Or someone cake ready? Right. Oh, they're coming up. 5 minutes should 37. 2 more times. 37. 1 more time. 37. You all happy with that? Is that good? Okay. So you can start to see these concurrent collection types that they created allow you to write code that is relatively simple. You saw how complex that stuff previously was, double check locking, making sure you lock things in the right order. It massively simplifies the code. We're going to take this further. At the moment, we kind of have to know, when we create the repository, it goes to the file system and it preloads the dictionary with all the possible files that are inside that directory. Once it's coming through a new CSV file, would we see it? No. So what we really want to do is move away from having a pre-created dictionary now to something that's a bit more dynamic, such that if a new file doesn't work on disk, we can deal with that and cache it too. Okay? So we're not going to deal with a regular dictionary here, because the problem with a regular dictionary is not thread safe. And that creates issues for us, you see. Because if we didn't initialize the dictionary, so scroll down a bit. If we just had the dictionary there, it's completely empty. So we just initialize the CSV files to an empty dictionary. What would our code have to look like? It would be very dynamic. If the dictionary was empty, what would we have to do? When we get asked for a CSV file, we have to say to the dictionary, is it in the dictionary? And the dictionary will say, no. If it's not in the dictionary, we could load it and add it to the dictionary. We want to make this thread safe, what are we going to have to do? Put a lock around all accesses to the dictionary. If we want to give it all race conditions, we have to lock, is it in the dictionary? Yes or no. If it's not in the dictionary, then load it. What we can't do is say, is it in the dictionary? No. Load it, lock, and add to the dictionary, because we know that sucks, right? Because there's a race condition between those two things. So rather than using a regular dictionary, we're going to use a concurrent dictionary. And the concurrent collections, concurrent dictionary, concurrent queue, concurrent stack, concurrent bag, they're very similar in intent to the regular dictionaries. The difference is they provide APIs that are concurrent. They never block. But the other big thing is they provide bigger building blocks. Rather than you saying, if something's not in the dictionary, then add it, it's like a method that says, get or add. If it's not in there, add this. If it is in there, give me whatever was added. Far bigger building blocks that happen at a high level of atomicity? Yeah. Okay, so new one of those bad boys up, quite a new line. Yeah. Okay, so wow, how many chevrons in the demo? Right. Okay, concurrent dictionary string. Yeah, okay. So we've got concurrent dictionary now. Okay, if we scroll down here, keep going down, where is it? Swap. Okay. So there's a couple of things we can do before we get carried away. In that files, that returns all the files in there. Can you just go in? We obviously can't do that, it's going to be empty. So can you just, that get, can you get rid of the return value? In the difference of value, new directory info, bracket quote, CSV. Dot select, thank you. FI goes to FI dot name. Name. Yeah, so every time you ask for the files, it's going back to the files. Cool. Okay, so that. Good. Right. So inside here now, we're going to use a concurrent dictionary. And yes, we could say to the concurrent dictionary, what was it called? CSV files? Do CSV files? Dot. Okay, you'll see here we've got things like add or update. Add something to the dictionary, or if your something's already there, replace it with what I've got for a given key. We've got triad, not to be confused with Chinese mafia. Okay? Try-add operation. Try and add it to the thing. If it's already in there, don't throw an exception. That's what would happen with a regular dictionary. If you try and add something with the same key, it goes bang. But because this is concurrent, another thread might have just got there just before you. So if you try and add it, it's already there. It says, you know what? Sorry, a bit late. Returns false. Okay? So it's a more non-blocking kind of API, and also trying to aggregate things up here. So the one we're going to use here is get or add. So what we're going to do here is go and create for me a lazy object of list of string. All right? So remember, lazy object is cheap to create. We don't mind creating these dudes. They're really easy. Right? Not lazy CSV. Lazy of list of string, right? Yeah. Okay, and give me the function in here. And it goes to load data. Data file list. Excellent. So that creates a lazy object. And then what we're going to say here is lazy equals CSV file get or add data file, comma, lazy. Okay, so what's this going to do? It's going to go to the dictionary, say, dictionary, do you have something with this key? If you do, give it me back, and that's what we return here, overriding our previous lazy. If we were the first to be there, okay, then it basically will put our lazy object into the dictionary. And then here we're just going to simply say return here, you've got this, you want to change that to lazy. Okay. Turn lazy, you're going to comment that out. Yeah. Mm-hmm. Yeah. Okay? So now we've got a concurrent dictionary that says the dictionary starts off with nothing. As we say on the CSV file, it will add to the dictionary. If two threads ask for at the same time, we're still only going to get one entry in the dictionary. And when you create the lazy object, it's cheap. Yeah? If it's already in there, you get returned it back. And when you ask for the value, if someone's already come and processed the value, you'll be told to. Well, this is easy to read. It's not hard, right? When you're in the semantics of lazy, this gets really nice and easy. Compile it, run it, ship it. Magic 37. 37. How cool is that? Okay. So you see, you can do some quite complex things here. Ask if it's in a dictionary. If it's not in a dictionary, go and add it, and then get lazy back, and then do queue up behind it to say, give me the value. Any questions with that? All good? We're almost on schedule. So the concurrent collections was introduced in terms of .NET 4. Concurrent dictionary. Anybody use concurrent dictionary? Really? Have you been disappointed with concurrent dictionary? Yeah, in .NET 4 it sucked, particularly for inserts. If you do a lot of inserts into it, it really sucked. Okay. So there's performance issues. They massively changed it in 4.5, so it's a far better performance. And there's some things as well you can do in order to make it a little bit easier to handle in performance. If you create a list and add 1,000 items, it takes a certain amount of time. How can you make it quicker to add 1,000 items to a list? Very good .NET list. How do you make it quicker? Set the capacity. You see, the problem with the list is, how big is in a list initially? It's a vector, it's an array of how many items do we know? I thought it was 10. I might be wrong with 11, I can't remember. Once it fills up that 11, what does it do then? It then creates a new array of how big? Let's just say it's 11 for argument's sake. How big is it then? 22. Once it fills that up, how big is it again? If you don't know the answer, you're probably getting a pattern here. 48? Yeah. 48? 44. Thank you. He's got the maths degree, I have. Okay, so 44 doubles, 8, etc. So it doubles in size. But obviously each time it needs to grow, it needs to copy. That's obviously expensive. So if you know ahead of time how big a list is, you really should move the list up to be however big it needs to be. The same kind of rule applies to concurrent dictionary. So we've got concurrent dictionary here. With concurrent dictionary, we've got, what was it there? How many numbers have I got there, Rich?
10 million.
10 million. We've got power.4. I'm going to have probably on this machine somewhere between 4 and 8 threads, all trying to add some value to that dictionary. The total number of adds will be 1 million, 10 million, or whatever it is. To the add, we've got lots of threads trying to do this. Okay? I'm not telling you ahead of time how big the dictionary is, they run the code. Okay, put task manager, let's just see make sure everything. That's dropping off quite a bit. I should be coming in. There you go. It took 11.2 seconds. If, however, we say to the dictionary, we know how many items are going to be in this dictionary. We can move this up. There's two things you have to give it though. A capacity, which is what you do with the list, but also the number of threads likely to be accessing this dictionary at a period of time. Yeah? So this is there for allocating blocks for contention. So I'm going to say 4, okay, comma, number of numbers. Remember, 10 seconds is the number to beat. Run the code. That's a hell of a speed difference, right, from 10 seconds. So the concurrent dictionary, just bear in mind, you really need to be thinking the fact that if I know ahead of time how big it is and how many threads I think we'll be accessing, give it a hint, and it will allocate the data structure ahead of time and I'll hopefully give you by far better. Okay, I haven't touched the other slides, but okay, so let's look at power. Parallel tree was great. So, there is a concurrent queue. That is a thread-safe implementation of what are the data structures you probably know. Queue. There's a concurrent stack. That's a thread-safe implementation of stack. There's a concurrent dictionary, which is a thread-safe implementation of a... You're not playing the game, right? Then there's also a concurrent list. No. It's not a concurrent list, there's a concurrent bag. What's the difference between a list and a bag in computer science? Order. Does order matter? A list preserves order, a bag doesn't. Put 2 oranges, an apple, a banana into a bag. Say, can I take something out of the bag? Could be the banana first, could be the orange, could be the apple. What you do know is if you ask me for 5 things, you will get all things out eventually. Okay? There's no order that's guaranteed. So concurrent bag is there, but there's no concurrent list. There's no concurrent data structure in the framework for preserving order at this point. So they have a concurrent bag. They didn't do this. If you care about order, there's 2 other types, concurrent queue and concurrent stack. They will preserve order. So a lot of people think, well, if I just need a data structure, good. All I want to do is store values produced by multiple threads in a thread-safe way, I'll use a bag. It's not a good plan. So a bag, the way a concurrent bag works is this. If I have 2 threads, okay, and I want to share a concurrent bag, I could have one set of memory that both threads here were fighting over to stick stuff in a thread-safe way. But that creates contention. So a concurrent bag works like this. Each thread that wants to put something into the bag actually has its own little private bag. Okay? That only it generally puts stuff into and takes stuff out. So each thread is part of a big bag, but it has its own little private bag. And it sticks stuff in its little private bag. So you say add, it goes into the private bag. When it calls take, it takes stuff out of its little private bag. But when its private bag is empty, what does it do then? It steals. Just like when you were in a queue, you eat all your sweets out of your bag, you tell your brother, look over there, and you steal stuff from his bag of sweets. That's exactly what it's doing. That requires contention. Okay? But the idea is, if you can write your threads so they use their local mini bag as a priority, then life is good. So the place where this really comes to play is standard kind of parallelism like in Concurrent. So if I kick off a thread with a piece of work and it wants to break that down into smaller work items, it can add them to a bag. Once it's added them to a bag, it can then say take something. We can start working on it. And that item then might get divided again and puts more sub-items into the bag. Another thread will be doing the same. But if it runs out of work, what's it going to do? It'll steal work from someone else. Okay? So that's the common model. He's been busy writing code while I was... what are you doing?
Well, I was trying to say current bag of bags rather than current bag. That's all the scripture bit is.
A Oh, jeez. I thought you were doing something useful. Now I'm behind. Right, let's go to the code.
That's what we're going to do.
Right, so no, we should have done this. Program.cs. Okay, scroll down. There's a fair bit of code. Scroll again, scroll again. So what I've got here is a parallel tree walk. Okay? It wants to walk a tree of nodes. Nodes have children. Yeah. Each node can have children, etc., etc. As it walks the tree recursively, rather than using stack-based recursion, it uses some kind of heap. So it opens up a container, acts on the container, and then all the children it puts into a heap. Add. Once it's added them all, it goes back around the loop, says give you the last child I added, potentially, take that one, process that. Does it have any children? Add those to the heap, etc. Okay? So, we've got an implementation of the heap. Just jump to that. This node heap adapter. Okay, so it's relatively simple. As it's walking the tree, if it sees a node, it adds it to the list. Yeah? To get it, let's set children, of course, try take. And looks inside the list of children. If there is one, it takes it out. Yeah? All good? But obviously, this is going to be happening across multiple threads. Okay? I'm using a regular list. That's all up. So I'm just using a regular list for this. Okay? Class program.cs. Scroll down. So we've got two versions. Parallel walker.do, that's running on a single thread. And we've got parallel walker.do async, that's running on 4 threads. Okay, and it's effectively going to try and process the whole directory structure on 4 threads. What directory am I looking in? Is it C++10? Run again. So it's going to run, it's going to give us 2 times, one for sequential on a single thread, and another one for running in parallel. So it took 9 seconds. We're on a single thread, 4 calls, what do you reckon? Showing 8.7. This isn't good. There's high contention here with the lock. Okay, however, through the power of the copy and paste, which is going to do really quick. Okay, we're just going to rob that code. Scroll up. Now this is going to be a concurrent bag. That's what we're talking about. Yeah, it's going to be a concurrent bag heap adapter. So instead of having a list here, we're going to have a concurrent bag. Concurrent bag is perfectly thread safe. Yeah, just the same as concurrent dictionary. So let's go concurrent bag. Keep that. Concurrent bag. So yeah, you got it. Okay. Okay. And change that to new. You can go such way. Just new equals a new concurrent bag. Pass it into that. It will initialize from line. Cool. Scroll down. Get rid of the lock. I need it. It's concurrent. Yeah. Scroll down. Try take. That's part of the API as well. So get rid of the whole of that code. And say return to adapt. To adapt. Adapt. Try take. Add. No. Okay. So we're just using a concurrent bag. Okay, that's the program.cs. Change our code, so instead of using one of those bad boys, comment that line out. Okay, we'll change it, it's fine. Okay. Alright. Compile and run it, ship it. Hopefully now. Well, I should just take back the same kind of time for the sequential one. Well, maybe it's cache groups. Okay, but the important thing is, okay, now we're down to 1 point. That's a massive scale. The concurrent bag is not a general purpose place to stick stuff. It's really designed for when you're dividing work up. And when you put stuff into the bag, if you're the most likely person then to consume from that bag on that thread, then this is the data structure for you. It's not a general purpose collection. Alright? Cool. Right, let's go. Okay, so some more questions. Let's go to producer consumer. Let's do one more example out of 15 minutes. Can we do this? Yeah. So, producer consumer pan. What is that? We have a queue. We have a producer that puts stuff in the queue, and we have consumers that takes it out of the queue. Woo! Okay, you can see the demos are getting more excited as we go. So, go and create me a concurrent queue of is. Okay, and let's do this. Go and create me create me a task with that. Consumers, okay, one. Yeah, goes to consumer and passing queue. Consumer. So you really want clipping, don't you? Think you're right, the method. Would you like some help? That's what you would like, isn't it? Like it's detectors. Consumer. Yeah, so recommend. Okay, cool. And then create the method. Excellent. Content avoid. Cool. Right. So inside there, do a loop while true. Yeah. And inside here, we want to say q dot what? DQ? See, there might not be anything in the queue. Yeah? If you do DQ on a regular queue, there's nothing in the queue, what will happen? It will throw a exception. So you should say, if something's in the queue, then DQ. On a multi-threaded environment, that wouldn't be good, would it? Because between checking and DQing, someone else might have changed the state of the queue. So we just have this method called try DQ. Okay? And then do a sleep from there, which, well, a few seconds.
Yeah,
No, inside there. Yeah, inside there. Yeah, let's pretend we can bring something useful. Friend at sleep. Sleep. 5 hours. Excellent. Okay, all good? Yeah, and then after the sleep, say consuming again. Yeah. Excellent. Alright, cool. So we keep the 5 threads. They're all hopefully ready to consume. And then we'll do this in while true. Inside here, what we do, a console of region. Passing true. Every time which hits the keyboard, okay? Now what we do is put a timer around this, and as long as you hit the keyboard 5 times in 2 seconds, it will go down to secure. Can you do that?
certain people have struggled with one line.
Okay. And after this, if you just say, I don't know, Q dot, NQ, just NQ a random value. I don't mean just pick a random value, R&D for me, you know. Cool. Run. Okay, see them run? Run in. Okay, just there. Press the key. Another one. Another one. Another one. Another one. Hit a few keys hard. 5 in a second. So, we're queuing stuff up, right? Yeah, so things go into the queue. We've got how many 4 consumers busily working away? Are they all ready to consume again? They're all back to ready to consume alone? Yeah, we're getting close. Cool. We're going to pass mode. Is this good? If we're trying to warm up this already very hot room, this will be awesome, right? Or just trying to bring you coffee or something like that. This will be good. Problem is, why is this hot? Oh, we can do a hand gesture now, can I, Rich?
Yeah, sure.
Yeah. So this is spinning, isn't it? Because what are we doing here on the consumer? While true, try DQ. Is something in the queue? No! What do we do next? Try again. This is spinning here. Okay? This isn't good. You don't really want to spin. Okay? So instead of spinning, what do we actually want to do?
Wait.
Go to sleep, maybe. Okay? Alright? So concurrent collections don't block. But sometimes you do want blocking semantics because you don't want to be burning up thread sizes. Okay? So what we can do, instead of using a concurrent queue, we can use this thing called a blocking collection. Now a blocking collection actually will provide blocking semantics for any type that implements I produce a consumer. Yeah? Now produce a consumer is alright, or consumer.
Consumer protection.
Right, produce a collection. So I can pass into there a queue, I can pass in there a concurrent stack, I can pass in there a concurrent dictionary, and it'll give me blocking semantics for those different data structures. By default, if you just create an instance of a blocking collection, you don't give it anything to wrap up, it will automatically give you a queue. Okay? Right, so we'll be changing that, so we're going to pass around not a Q now we pass around a blocking collection. There's no try DQ. This is a general purpose thing to wrap up stack, concurrent stack, concurrent queue, concurrent dictionary. All it allows you to do is a take. Okay? Yeah, and then if it's a concurrent stack, it's going to be a LIFO kind of thing. If it's a concurrent queue, it's going to be a FIFO kind of take. Okay? So at the moment now, that's effectively in a block. Yeah? So we call take, that blocks. So have you changed everything now? Change the producer? So because he hadn't changed the producer, this would not have worked. Right? Because effectively, you need to, the thing you in Q2 has to be the blocking collection. That's how it signals to know that something needs to be working out. Right, good. Okay, component relationship. Okay, we have a task manager. Okay, so now all those 4 threads are running. Give me some work to do. Okay, amazing the time they're sleeping. Yeah, but then eventually when they all come back to ready, we're going back to 0%. Yeah? All good? Okay? One little tweak you can do. Can you all see that? Okay. Rather than doing while true down here, change the while to for each. Yeah, so there, change it to blocker. Get consumer. The blocking collection does implement iron directly. If you do an iron inward in the blocking collection, it will tell you all the things inside the collection. But if you want to consume them as you for each them, you need to get a consuming them. And just move that body code. That's exactly the same. When there are no more items to consume, it will block here. Yeah? Okay? Obviously, if you want to say there's no more ever coming, there's no point you waiting, and we need to find a way of signaling. The way we do that is inside here, go and check it, look at the key. So if you just do it different, it's cheesy. Console key up here. We did rekey dot key, sorry. Then so the blocker complete added. So when we press the Q key, we're now saying there are no more items coming. Okay? Scroll out to the consumer. Yeah. And just print out after the for each all done. Okay. At that point the task will end. Scroll up. Yeah. And then just break out our wall. And then after that, just do a task start. Consumers, task start wait on sorry, task start.
If we carry on try to add something else to the
it will go boom. Yeah. If you call complete adding on a block collection, you try and add it, goes, valid operation. Press the Q key.
Yeah.
How many items did you add? You didn't count them. So we couldn't wait here for ages, couldn't we? All done. Yeah? All happy with that? Yeah. So that's blocking collection. So that's pretty much the state of play things were around about .NET 3. So what we're going to look at now is we're going to change it a little bit. We introduce this idea of what's called immutable collections. So let's go to that new project. Immutable sets. Okay. Can I program this yet? I'll give you the script. Okay, so here we've got this object called a bank. Okay? And a bank has lots of money in it, hopefully. Accounts. Okay? It has accounts. So we're going to create an instance of the bank with 10,000 accounts. Each person's going to get given £100. Okay? Yeah? It's birth of a baby, they'll get £100. Is there stock there now? Do you still get £100 if you have a baby there? There's a chance they'll not give you that. Okay, so create an instance of a bank, and we're going to initialize the bank. Okay, and then we've got one thread here. Oh yeah, so we're going to sum up the total amount of money in the bank, and we've got a thread here. What's this thread doing? It's randomly picking bank accounts and moving money around. Okay, so if you're lucky, you can earn more money. If unlucky, you might look at less money. But anyway, that's what's happening. So all the transfers in the bank are internal. So at any point in time, how much money should be in the bank? The same. Yeah, exactly the same amount of money. Okay. So we've got to know, if we run the code, we've got to know where true is. Okay. So what we do is we're going to write a little thread now to true balance. Whoa, after that. Task.run. So task.run came out in .45. Prior to .45, we had task.fetch.start new. We thought that was a bit long-winded. So now we have task.run. That creates a task. It's constrained, don't get all the names, saying the flexibility of task.fetch.start new. It's just a quick and easy way to create a task. Okay, inside here, we need to do what? Well, this is an audit thread. It's going to constantly be auditing the bank. And it's going to calculate the total amount of money in the bank. The way it's going to do that is going to log that code. Not the variable. Okay. We say actual money in the bank. Yes. Okay. Yeah, we can use the var keyword, the evil person. Just do it actual. They don't care either. Okay? Right. And then we just have a little simple. After that, can you for me? Let's do this. If, no, then do this. Console.write. Console.write, sorry, not right. Okay. Actual money in bank, double equals. Double equals. Total money in bank. Question mark, or a dot, or a column, exclamation mark. Cool. So, if the right amount of money is in the bank, get a dot. If the wrong amount of money is in the bank, get an exclamation mark. Yeah? Okay. So, go and have a look at the bank class. Let's just show them all the lovely juggins. So, here's a bank. It has a annual accounts that returns you the accounts. Here we have the transfer fund option. Yeah, it just basically does what? Passes the two source accounts and just moves the money around. Okay? There are two threads at play here. One is reading, one is writing. We're going to have a problem. Yes, we're going to have a problem, aren't we? Yeah, let's go run the code. We've got quite a few. Occasionally, we get a dot. Life is good. But on the whole, I think you're fair to say it's not good. Okay? So how do we fix this? Could we use a lock? Let's throw a lock in, Rich. Lock on accounts. Okay, all good? Anything else you got a lock around? What? Anything else? Is that it? Is that going to fix it? Well, on the reading, right? So we're going to stick it inside the rebound and return. Yeah. Second one?
You need a tier list or something.
Oh, you need a two list. Put the lock there. Okay. Whoa, that's a big lock, isn't it? That's a big ass lock. So if we want to lock in, what are we actually locking? We just lock in and return the reference. Still, the list is still being safely accessed, right? So that's not working good. So you said at the front here, Gareth said, to list. What are we now locking now? We're copying the list, aren't we? Yeah? Is this going to work? Part of it. Now, what do you notice? It's slow, isn't it? You can actually soak in all these exclamation marks. That's definitely slower. So, we're copying it. What are we actually copying? When you copy a list, you do this, what are you actually copying? Make another list that points to exactly the same objects as in the previous list. This is not good. We want to have a deep copy, really. I mean, is the right place to copy when we do the read operation? Probably not. It may be when we do the write operation. Maybe that's the thing we don't do very often, maybe. So we probably want to do the copy here. So inside here, Rich, don't do a two list on that. Go back to get rid of the lock. Get rid of that. Actually, no, let's get rid of it. Let's get back to it. Just return the action. And return the list. Return it without the two lists. What we'd like to do is safely manipulate the list. The list requires two operations. Yeah? Extract from one, add to another. As far as the outside world is concerned, they should only see the state of the bank prior to the transfer and after the transfer. The standard way of solving this transactional problem in C++, and we know the acronym which gets used. Pimple, pointed to implementation. Inside here, we're going to take a copy of the list. So we do exactly the same thing here, accounts. Now the thing is, we can't just do a shallow copy here. We've got select. A goes to new account. Passing in, A.id. Right. So they say balance equals A.balance. Close bracket. Do this. What's that called? Keep the loop. Do this. Look at our separate line. So what we're doing here, we're actually creating a copy. Get rid of the lock. We're only going to have one thread ever doing this, so we're not going to bother with the line. Okay. Now what do we need to do? This bit down here, the pimple, the accounting, we shouldn't be acting on accounts, we should be acting on pimples. Yeah? Excuse? And then here we say, once we've done it, we can say accounts equals. So we shouldn't be saying the accounts is currently pointing to this state of the bank, and that points to that state. That's an atomic operation. Perfectly safe for us just to flip that across and that. It's going to work? Should life be good now? Go ahead. Brilliant. Perfect. And that works. But it kind of sucks, doesn't it? Because why are we having to copy every time we move some money around? The entire list of all the accounts in order to make this happen. If I only want to modify one or two things, that seems like a lot of overhead in order to achieve that. And that's where they came right in .NET 4.5 as part of the NuGet. Microsoft released what's called immutable collection. Your ability to work with collections that are immutable. If they're immutable, you can give them to someone, that means they will never change. Now, they could have implemented immutable collections in a way that when you add stuff to a list, it copies the previous list and produces you a new list. Would that implementation have been any good? That would have sucked, right? So what they prefer you to do, or in this particular case, is they will share as much as they can from the original list. Okay, so they'll try and build a new list, but sharing as much data from the original list. Okay? Just do a quick simple example. Flip to Chrome.cs. I'll re-download the NuGet stuff. Now, how do you normally create a list? You new it up. You don't new up an immutable collection. Okay? Here we say immutable list. Okay, so there's different ones. There's a immutable queue, there's a immutable hash set, there's a immutable dictionary, immutable list, there is an immutable tree. I'm trying to work on that. There was an immutable array, they called that. Yeah, let's do it with integers. I don't know, primes. Equals immutable list, no new, immutable list of int dot empty. Okay? Okay, and if you do a for each over that, for each, yeah, primes. Yeah, int. There you go, sharper. Isn't that cool? It's all primes, takes the S off, creates a variable. Okay, if we print out on the screen, unless there's some magic going on, we compile a season using a variable called primes, we won't see anything. Agreed? Yeah? So let's do this. Primes.add. First prime number? 2. We have a slide with the 1 on. The mathematician that we make the list. Okay, 2. What's the next one? 3, 5, 7, 11. Run the code.
Rubbish.
rubbish, isn't it? So clearly you can add, because the compiler lets you do it, well, remember we said it's immutable. You know, we're trying to add the empty list 2. Well, the empty list can't have 2 in it because it's empty. What we have to say here is primes equals primes.add. Yeah, let me get rid of you could write equals lots of times. We can primes.add returns what you think, and a mutable list of integers. So it returns you a new list. Like I said, if you copied physically, that would kind of suck. Because you could write that yourself, it wouldn't be hard, that's what we just done. What it is actually doing is it's trying to share as much of the data structure from the other lists as it can. You can remove, you can add, and that. So there's some slides I might show you that shows how to do it. Now we run it. Okay? Yeah, so effectively we're just adding to this collection. Okay, so that's what we're going to do with the bank account. We want to move the bank account now, so instead of us making a copy, we're actually going to use immutable collections. So, where are we? Back in the bank? Okay, so let's modify the bank. Let's change that to immutable list. We'll change that to an immutable list of accounts, and it's going to be initialized to okay, so that's what we're trying to do. Right. So inside here now, comment. That's what we had before. We took a full copy. What do we want to do here? Logical. We want to remove the source account and the destination account and replace them with what? New versions with a new value. Okay? Yeah? So, yeah, different account. Now, the thing is, we're using an immutable list, but the things that we've got in the list, are they immutable? No, the account object has a balance with a getter and a seller. It's not immutable. So really what we want to do is try and, if we're going to use immutable collections, we often want to put the types in the immutable collections themselves to be immutable. Otherwise, in real sense, the list isn't immutable, is it? Because the two lists, the list can't change in terms of the references, but if the content can change, you could argue it's not really an immutable list. Okay? There's a kind of standard pattern of how you build this kind of stuff. So did you kind of work out that? So make the balance private. Private state. This object now is immutable, correct? Yeah? And if all our bank accounts are like that, we get pretty annoyed. Well, maybe not. If you start off with 1,000 every time you did a debit, it didn't take any money out. That would be good. But we want to make this an immutable version. There's a kind of standard pattern here. The way we do it is this. We create a method called public account with credit. And that takes a decimal. That's the credit amount. What's that going to return? It's going to return an account. This is the point where we make the copy. So when you say to the account object, I want this account object now with this credit applied to it, it will return you back a new account object with the credit applied. So internally it will do balance. No, don't do that. Equals balance dot. Sorry, don't start with plus. No, you use it right, balance plus. Okay, sorry. And then finally, we look at debit. Okay, and then that's marked. Okay? Yeah, so you can see now that, go back to our program CS, let's do this manually so we can see this working. Yes. Do you still have the old main name stuff, or do you rename? Yeah, just, yeah, okay, old main name. Probably another one. Let's do another one. Okay, so if you want to initialize an account now, we can say account equals I give an idea of balance. And then what we can say, if you say ACC dot with credit, 100, debit 50, and you can have balance. Yeah, so we should end up with what? We count the balance of 50. Yeah? Okay? Yeah, all happy with that? Yeah, well, good. Good. So that's the rename that, and let's go back to where we were. So with that, and the reasonable list, we should be able to solve this whole transfer issue. So, we go back, and then you've got some new questions. Right, so what are we going to do? After you've done the source and nest account, what do you want to do? We're going to do this. Accounts equals accounts. Next line. Dot what? Remove source account. Yeah? Dot remove desk account. I'm going to take them out. Yeah. Dot add source account. Dot with debit of amount, was it? Yeah, amount. Next line is add desk account. Dot with credit. Yeah? Under the covers, it's only copying what is necessary in terms of the list structure. Is that a thing of beauty? I think that's quite nice. Yeah, it's perfectly fair to say. No locks hurt in this process as far as we're concerned. Yeah? We're just declaratively saying, produce me a new list with that account removed. Now that one removed. Oh, and add that one, and then effectively we got a new set. We got a new reusable list, which is what we're exposing to the outside world. Okay? Run the code. Whoa! What did you do wrong?
If you remove something, if you remove the one before the other.
No, it shouldn't make any difference because you're removing the object, not by index. Oh, thank you. Yes. God, I remember seeing that at one point. No. Let's do it properly. Go back to the random number generator. Any program is fine. No. The source is not equal to desk, so that shouldn't happen. Yeah, I remember seeing that on Chestnut. Let's run it again. Hit F5. I've not seen this before. Hit F5.
Just when you're finding, when you look well, I did the change in tree.
Yeah, but it should always be the same number.
Treat those two lines, and the others can.
Scrolling up in there.
Oh, I know what we haven't done.
Go and populate it.
We haven't scroll down. There's a bit of code populated. Spot the error. Scroll across. What's the error? Yeah, so just adding it, we're going to end up with an empty one. Yeah, so go back to the add code, just scroll down. There you go. Accounts equals accounts dot add. Like that. Yeah, otherwise just there's never any accounts. Okay, all happy? So immutable collections seems like the most awesome thing on the planet. But are they? So let's go and do one last demo. Let's go and look at performance. That's what I'm at. Okay. Let's look at results. Okay, here we go. Who likes football? I hate it. I think this is brilliant. Hands up if you like football. There's a few of you. I've heard it's quite popular generally. You normally get more than that. Okay. So, this is supposed to be simulating a football website. There are football matches finish and results get added to the cache. And mad football fans, like a few out there in the audience, constantly hitting the website saying, tell me how my team's doing, give me the latest scores. Here's a very simple implementation. A match result has two teams and the scores. Scroll down. We have a results cache abstraction, returns a list of that, keep going down. And then we have a very nice little link statement, get results. Okay? You pass in your country, this is European football, and you go and find any match your team was involved in and return the result. Okay? Return terms of all the results that match your country. Yeah? Go back to Program CS for that project. Cool. Scroll down. What we're going to kick off here is we're using the simple results cache. We're going to have Richard press the R key. When Richard presses the R key, that's the point where we're going to insert something into that collection. It's going to be a fantasy result. So if your team didn't do very well, I'm sorry, it's random. Okay? We've then got 2 threads, create readers, cache readers 2. 2 threads are constantly reading, yeah? Simulating you mad football fans asking for random information. Run the code. So we've got 2 threads running, each thread is currently processing around about 4,300 per second, roughly, yeah-ish. Richard will press the R key. Oh, there is no thread safety code here. What's the exception? Well, basically he was modifying the collection, right? Okay? Yeah, how can we fix this? There's a hint, we just done it. We could be using the immutable one, couldn't we? And in fact, here we have. I didn't want to waste my time writing it for you, but here it is. This is an immutable results cache. Yeah? We're going to create an immutable list. Yeah? We will get results. We're going to do it against the immutable list. This collection can never change. Therefore, you can enumerate over it without any danger. Okay? And here we go. Immutable list. Immutable list results.add, and we reassign it here. Okay? All good? So, go back to, let's change it. Hopefully that's straight. Go on, So, the results work. Is thread safe? What about performance? Does it rock? This is bad. It's not good. You've got to bear in mind, the way this stuff works, it's about sharing as much data. They don't store a list, yeah, as a contiguous block of memory. It's a linked list. They're moving, they've got pointers pointing around. They're trying to share as much of the data structure as they possibly can. Therefore, walking through these things are way more expensive than a conventional list. Okay? So immutable collections are great for scenarios where, particularly in UI, if your user needs to go through some complex data, and you need to be rebuilding it behind the scenes. What you don't want to be doing is doing what's the UI. Pausing it. They allow you to do that kind of stuff, but keep that interaction. The UI environment isn't necessarily about raw performance. You're not, this is like 2 threads constantly banging that link query. Okay? This isn't for that. If you're still interested in that kind of stuff, well, we probably need to revert back to just paying the cost of a copy. So let's do it real quick, Rich. So if I want this to go really quick, we can make it thread safe. We can make it immutable. We're just going to roll it ourselves this time. And we're going to take a copy, because most of the time we spend our time doing what? Reading. Well, reading. How many are using 2013 at the moment? Have you seen issues? Projects that suddenly don't compile, they come up with some weird target issue. We've had some weird things, haven't we? Okay, let's get back to life. Let's just go and quickly replace this. Okay. So all we're going to do here is just do a manual copy. Right? Match result, new results. Okay, yeah, new ones, yeah. Pass in the old ones. Yeah. And then pick it like that. No results. Okay, and what's that? Would you call that one optimal? Yeah, let's hope it is, Rich. Okay, and we change this now. Remember, we've got 4,000 we have to get to, yeah? Yeah, we're pretty near enough. Okay, is it thread safe? Yeah, it's still thread safe. Yeah. So if you're only occasionally writing, and you don't mind making a copy, and you spend a lot of time aggressively reading these data structures, immutable collections are not for you. They're not tuned for high performance reading. Yeah? They're designed for about you being able to update something. The origins of immutable collections, anybody know where they come from? Well, I'll show you. they're basically the Visual Studio team built the Visual Studio for things like IntelliSense. So as you're typing away and it's having to compile in the background, it's modifying the code DOM. You're not rebuilding these structures all the time. They have immutable collections that you can run syntax analyzing against that kind of stuff. That's where it comes from. But they were nice enough to say they were useful to us, making them useful to you. That was the plan. Okay, we've covered a lot. I guess go. We've covered these. Go. Okay, go. We haven't really talked about asynchronous collections. It's a bit tight on time. I mean, this hasn't really come big time at the moment, but a lazy of T, for example, lazy of T, if multiple threads are waiting for the value, they'll all block. Really what you probably want to do is not return a lazy T, a lazy of task of T. Right? And then you can await on the value, which means you give up the thread while the other thread's building it. When it's finished building, you get the thread back and you carry on. So there hasn't been a lot of work on this, but I think this is going to start happening in the future. Immutable collections, yeah, we can take copies, but what we want to try and do is share as much of the data structure as we possibly can. So here's an example. This is the original list. Yeah? And if I want a new list where I insert this new node D, then at the end, then this list, new immutable list, contain a pointer to that one, and when you finish iterating through that, it will then attach that one to the end. Okay? So it's a linked list kind of model. Similarly, you can, if you want to remove items, then effectively we can produce a new version of the list with removing the items. But trying to share as many things. So this new list still has A in it, so it still contains A. It has to have a new node for A, but we're still sharing that piece of data, and obviously then this links to that one. Okay? If that one's linking to other things, then you get a new list, sharing all those stuff. Okay, so thread safety is kind of important. We want to write code that runs across multiple threads. We want to be safe. We don't want to be too safe. Right? We don't want to be so safe that everything ends up on a single thread. We want to try and use sophisticated locking algorithms in order to maximize throughput. The problem is if we do sophisticated locking algorithms, our code starts becoming unmaintainable and hard to read. The concurrent data structures, the immutable collections coming out in 4.5 basically allows you to write simple code and let some other smart, geeky dude worry about low-level locking. And hopefully your code is easy to read and at the same time you get some performance. Okay, any questions? Nothing. You all want to go for coffee, don't you? Ice cream. Is there ice cream? No. Be good though. So thank you very much for attending. If you've got any questions you want to do afterwards, please feel free to email me. If you want to know more, we have a book, okay, which all this goodness is compressed into a book. And I have
Yeah, you got it.
a copy. Anybody want a copy? Okay? All right, thank you very much.